As we said, law structures are the simplest, easiest, and most useful way of describing covalent bonding. It will give us a lot of information about the structural composition of the compound, and we'll learn what type of information we will get as we go forward. But let's start with how to write them. First step is add up all valence electrons of all the atoms in that molecule and get the total number of valence electrons in the whole molecule. Second step is going to be drawing a skeletal structure with the least electronegative element in the middle, except hydrogen. Hydrogen is never in the middle. So you put the least electronegative one in the middle and surround it with the most electronegative ones. And then you start filling the octet rule or satisfying the octet rule for the outer atoms first. After you finish the outer atoms, you move inward to satisfy the octet rule for the central atom. And depending on how many valence electron you will have, is gonna tell you if you need to make multiple bonds or not. If you run out of electrons, you will need to make multiple bonds, and we'll learn what does this mean and how we do it as we go through some examples now. So let's start with this example here. NF3. If you count the number of valence electrons, nitrogen is 5. 3 fluorines, each one is gonna have 7, so 3 times 7 is 21, a total of 26. You start, the second step is drawing the skeletal structure with the least electronegative in the middle, which is nitrogen in this case. And then you surround it with the other atoms in all directions. And you start forming at least one bond between each one of the atoms and the central atom. To make these 3 single bonds, you already consumed 6 valence electrons. So you're left with 20. So you had a total of 26, used 6 of them to form the single bond, you're left with 20. You start distributing the 20 bonds on the outer fluorine atoms first to satisfy the octet rule. 2, 4, 6, and it already had 2 from the single bond, so that's a total of 8. Repeat the same thing. You will put 6 on this one and 6 on this one. Already used 18. That leaves you with 2 electrons, and that's exactly what you need to fulfill the octet rule for the nitrogen in the middle. Let's do a couple of other examples here just to make sure we understand how we do it. For ammonia, what's the first step?
You would put the nitrogen in the middle.
The first step is counting how many total valence electrons we have. We have 3 hydrogens times 1 electron each. That's a total of 3. We have 1 nitrogen times 5 electrons, 5. So that's a total of 8 valence electrons. Second step is drawing the low structure, the skeletal structure with the least electronegative atom in the middle, except hydrogen. So we cannot put hydrogen. Then we start distributing the valence electrons so that we fulfill the octet rule of the terminal atoms first. Just forming a single bond is going to be enough to fulfill the octet rule for the hydrogen. And that will leave you with 2 more valence electrons that you just place on the central nitrogen to satisfy the octet rule for that nitrogen. Let's do one more example, carbon dioxide. What is the first step?
You find the total valence electrons.
Valence electrons. How many valence electrons do we have?
You have 1 times 4 for carbon, and then you have
times 4 is going to be 4.
2 times 6 for
oxygen times 6, that's 12. So that's a total of 16 valence electrons. So second step, what do we do? Skeletal structure with the least electronegative atom in the middle.
C.
So we put the carbon in the middle, 2 oxygens around it, and we start with at least a single bond. to bound the atoms together to form a molecule. And then we start fulfilling the octet rule with the terminal atoms first. So oxygen already has 2, so it needs 6. So you put 2, 4, 6, 2, 4, 6. How many valence electrons did we use so far?
14.
Is it 14 or 16?
16.
It's
Oops,
16.
my bad.
So we're not left with any more valence electrons. So is every atom satisfying the octet rule?
No. You need a
Carbon.
double bond.
So in that case, we have a deficiency in valence electrons. All what we need to do is just try to move a lone pair from an atom to make a multiple bond. In that case, it didn't change the number of electrons around this atom, but it just added 2 electrons to the central carbon atom. So carbon now has 6. It still needs 2 more. So we can move another lone pair to form a double bond, and that way we already satisfied the octet rule for the central carbon. So whenever you have a deficiency in the valence electrons, you just move lone pairs from one atom to make multiple bonds with the atom that has deficiency till it fulfills the octet rule. Okay, I have a question. Why didn't I just move 2 lone pairs from the same carbon, the same oxygen? Is there a problem with this?
Is less stable
Why?
because there is more attraction to one oxygen with the carbon than the other.
According to what we learned so far, there is nothing wrong with this.
It's a resonance structure, right?
Exactly. That's what we will discuss later on, is that in some cases, you will have a low structure that is okay, completely okay with the octet rule, but it's gonna be either not correct or not favorable, okay? That is called the resonance structure for the compound. It is okay with the rules, but it might have a problem that we will discuss later on. So that specific structure here is okay. It still satisfies the octet rule for each atom, so there is no problem with the rules. However, it implies one very important fact. If that's the case, how does the bond links between this carbon and this oxygen gonna compare to this carbon with this oxygen?
It's going to be a lot shorter.
A lot shorter, thank you. And that's not the case in reality. So if you got a molecule of carbon dioxide, you will have both of them at the same exact distance, which tells you that this low structure is not correct. The other one with a symmetric attraction between the 2 carbons and the 2 oxygen and central carbon is the correct one, okay? And we'll learn why in a minute when we discuss this. Let's just emphasize a couple of points that might make it a lot simpler when you draw the low structure. Is the number of bonds that each atom usually favored to make in a molecule. How many valence electrons does oxygen have?
6.
6. So how many valence electrons does it need to reach the noble gas configuration?
2 more.
2. That here is the number of bonds that it favors. So oxygen usually favors to make 2 bonds, which corresponds to number of electrons that it needs to fulfill the octet rule, right? If you apply this to nitrogen, how many valence electrons does it have? 5, thank you. So how many valence electrons does it need for the octet rule?
3.
3. So that is the number of bonds that it usually favors to form. Okay? Carbon, 4 plus 4. That's usually the number of electrons number of bonds that carbon prefers or favors to form in any structure. Chlorine, 7. So it just needs 1. So that's why it usually favors to form just 1 bond. So let me ask this question then. Which atom has an incorrect number of bonds around it? Is B. Can someone explain?
Because we were just saying that nitrogen tends to have 3 bonds, and in this display it only has 2.
Exactly. Carbon 4, nitrogen 3, oxygen 2, all halogens 1. So the only one that deviates from this is nitrogen. These are not like set in stone number of bonds that each atom has to have, but it's the most favored number of bonds around each type of atoms. And in some cases, it might form a different number of bonds. We will learn how and why as we go through some examples later on. Exceptions to the octet rule. As we said, all atoms are trying to fulfill the octet rule to gain the most stability, which corresponds to the electron configuration of the noble gas. But in some cases, it does not have enough space or enough electrons to do this. Something like beryllium. If you draw the low structure, if you count the number of valence electrons, you will see that it has only a total of 4. So there is no way you can make it fulfill the octet rule with 8 electrons. It does not have that number of electrons to start with. That's why the low structure for beryllium hydride is like this, and the beryllium atom is already fulfilling its own octet rule, which is 4 in this case. Okay. Same thing for something like boron. Boron trifluoride is a compound of boron. If you draw the low structure, you start with calculating the total number of valence electrons, which is going to be 24. That is going to be the correct low structure for boron trifluoride. Octet rule is fulfilled for all the fluorine atoms, but for the boron atom, you only have 6 electrons in total. Can we fulfill boron up to 8 in this situation?
1 pair on top.
Where you will get it from? You already used all your electrons.
Go bond with fluorine.
Thank you. We could have moved a lone pair from fluorine to make a multiple bond. So what's wrong with this? Why this doesn't happen? What did we say about the number of bonds that fluorine favors to form?
Fluorine's in the halogen group, so it would just be 1.
That's why boron is actually violating the octet rule with an exception. Most cases, all boron compounds will behave the same way. And same thing with aluminum. It's actually in the same group, so it behaves very similarly. In some cases, it can go the other way around, like violate upward, having more than 8 electrons, and is gonna be forced to do so. Something like that compound here, PCl5. Let's draw the low structures together. So phosphorus has 5. 5 chlorines will have 5 times 7. So that's a total of 40 electrons. So second step, put the least electronegative atom in the middle and surround it with other atoms using at least a single bond to bound them together. With that, you can clearly see that phosphorus is forced to, from the beginning, to have more than 8 electrons around it. It has a total of 10 right now. And there is no choice here. There is nothing that you can do to make it not have 10 electrons. And of course, you can finish the low structure by fulfilling the octet rule for the outer chlorines, put 6 electrons around each one of them, and that is going to be a total of 40 electrons already used up. Same thing for that compound here. How many total electrons, total valence electrons does this compound have? How many valence electrons does iodine have?
7,
How many for chlorine?
14, 7, 28.
Okay. Is that all?
No, you have a +1.
One more electron because of the negative charge. So negative charge is one more. So that is going to make it a total of 36 electrons. We draw the low structure, put the least electronegative iodine in the middle, and then put the chlorine atoms around it with at least a single bond. And then start distributing the valence electrons to satisfy the octet rule for the outer chlorine atoms first. So you will put 6 here, 6 here, 6 here, 6 here. How many electrons did you use total so far?
32.
32. How many electrons are we still left with? So we started with 36. We used up 32. That
Give me
means
4.
we still have 4 electrons remaining. Where should those 4 electrons go?
In the middle.
There is no choice. They will have to reside on the central atom. And if you count the number of valence electrons around the central iodine atom, you will find that it's 12. So it's way more than 8. Okay? And there is nothing that you can do here. Let's get back to resonance structure. For something like sulfur dioxide, if you draw the low structure, we do the same 3 steps that we learned. Calculate the total number of valence electrons, which is going to be 18. Put the least electronegative atom in the middle, which is going to be sulfur. Surround it with the 2 oxygens. And then start fulfilling the octet rule for each oxygen. You will put 6 here. And you will put 6 here. So that's a total of 8 for this oxygen, 8 for this oxygen. So you used 16 already. So you're left with only 2 electrons to put on the central sulfur atom. That makes the total number around this sulfur only 6. How can we make it fulfill the octet rule? In that case, form a double bond. But you will have 2 choices. Either form the double bond by moving this lone pair to form a double bond with this oxygen that will give you this structure here, or in the second direction, move this one to form a double bond in this side of the molecule to get this structure. Which one is the correct one? Both of them. They're equally possible to form, right? Either forming the double bond with atom oxygen 1 or with oxygen 2. And that's why we call them resonance structure, because the real structure is going to be a mixture of both of them, which means it's not actually a mixture of both of them. It's actually that the double bond is kind of moving from that side to this side and vice versa. Any given molecule will have that double bond 50% of the time on this side and 50% of the time on this side. What's the difference between having a mixture of 50% of the molecules with this structure with 50% of the molecules with this structure, in comparison to having the same molecule having the double bond split between the 2 sides? If it was the first case, we should have seen again that the distance between sulfur and this oxygen should be shorter than this sulfur and this oxygen. while it's the opposite in the second case, right? But in any case, the molecule will have two different bond lengths, but that's not real. That's not correct. In reality, any given sulfur dioxide will have the same bond lengths on that side as this side. So in reality, the real compound is going to be a mixture of the two resonance structures that might be best described like this, with half a double bond on this side and half a double bond on this side. We need to devise a new rule to tell us which law structure is more correct, and that is called the formal charge. Discuss this example here. Formaldehyde is an organic compound that is made out of one carbon atom, one oxygen atom, and two hydrogen atoms. If you think about it, it's possible to have the formaldehyde in that connectivity right here. You put the central carbon, oxygen, hydrogen, and the second hydrogen you attach to the oxygen, and double bond here, lone pair here, lone pair here. If you check the law structure, the octet rule for that law structure, you will find that it's okay, because carbon has 8 electrons, oxygen has 8 electrons, hydrogens have 2 electrons. So there is no problem in terms of the octet rule for each one of them. The problem is when you calculate the formal charge on each atom. Calculated formal charge is actually kind of calculating how many electrons actually belong to this atom in that molecule. So it's going to be the total number of valence electrons in the free atom minus the total number of lone pairs minus half the total number of bonding electrons. So if we calculate this for carbon, it's going to be valence electrons in the free carbon atom. How many valence electrons in a free carbon atom?
4.
Sorry, 4, yeah.
It is 4. Thank you. How many lone pairs around the carbon atom in this compound here? 1. So it has 2 electrons. 2 electrons in lone pairs, right? Then half of the number of electrons in bonding pairs around the carbon. So you have 2 electrons here, 2 here, 2 here. So that's a total of 6. So what would be the formal charge? 4 minus 2 minus 3. So it's minus 1. So it has a minus 1 formal charge. Can someone repeat this for oxygen?
Yes, it will be 6 minus
6
2
in the
non-bonding
free oxygen minus 2 in the lone pairs
minus
minus
1/2
half of
3.
6, which is going to be 3, right?
Yes.
So what would be the formal charge in this case?
-1
Plus 1.
or +1, yeah.
6 minus 5 is going to be plus 1. So it will have a plus 1 formal charge on it. There is a second possibility for an equally correct law structure in terms of the octet rule for that compound. It's this one. And instead of attaching the second hydrogen to oxygen, we attach to carbon. And it's actually going to make more sense, because in this case, we said carbon prefers to form 4 bonds. It does here. It didn't in the previous example. Oxygen prefers to form 2 bonds. It does here, and it didn't in the previous example. But more clearly, when you calculate the formal charge for that one, for carbon, it's going to be 4 minus 0 in lone pairs minus half times 8 So it's 0. Right? For oxygen, it's 6 minus 4 minus half of 4. It's 0 again. And instead of having -1 and +1 in the previous example, we have 0 and 0 in this example. So that takes us to what is the rule for formal charge. The most stable and most correct law structure is going to be the one with formal charge that is 1 as close as possible to 0. 0 is better than plus or minus 1. Plus or minus 1 is going to be better than plus and minus 2, and so on. So the closer you get to 0 value, the better or the more correct your law structure will be. Second, if you have a non-zero value, it has to make sense with the electronegativity. Negative formal charge is gonna have to be on electronegative atom and vice versa. Positive formal charge is gonna have to be in less electronegative atom. If we go back to the previous law structure for this compound, for formaldehyde, we had carbon with -1, oxygen with +1. This doesn't make any sense with electronegativity of both atoms. Carbon is less electronegative, so it should have had a positive formal charge if it is forced to have a formal charge at all. That is going to be very clear when we do the next example here. For something like N2O, clearly the arrangement will have to have a nitrogen in the middle and one nitrogen on one end and one oxygen on the second end. And then we will draw the law structure. We'll find that the first step is calculating the total number of valence electrons, and in this case we have 6 from oxygen, 5 plus 5 from the nitrogens, so we have a total of 16. So we start by drawing at least one single bond, put lone pairs on the outer atoms first. We already used all the 16 electrons that we had, but the central nitrogen is not fulfilling the octet rule yet. So what do we do in this case?
Do we double bonds between?
We form double bonds. Thank you. So we need at least 2 double bonds. So we either form all of them with the nitrogen, right? Or all of them with the oxygen, or we split it. One with this nitrogen and one with the oxygen. So which one is the correct one, or at least the most favored one?
Nitrogen, you said, usually has 3 bonds, right?
Yes, that's something that you can use. Thank you. But you will find that if you use this rule, you will find that this structure fulfills the number of bonds for nitrogen, but it doesn't fulfill the number of bonds for oxygen. This one fulfills the number of bonds of oxygen, and it doesn't fulfill it for nitrogen. This one doesn't fulfill it for either. So none of them really satisfy this rule at all.
I see.
At least completely. 1 and 2 partially satisfy it for one element or the other, but none of them completely satisfy this for all of the atoms, right? So here we need formal charge. And we need to remember the rules for formal charge. Most stable formal charge is 0. If you have to have formal charge, it has to be negative on the electronegative atom, positive on the less electronegative atom, right? So let's calculate formal charge. Let's start with first one. First nitrogen in the first one. How many valence electrons in a free nitrogen?
5.
5. How many electrons in lone pairs in that nitrogen here?
4.
How many in bonding pairs?
2.
It's 4. Half times 4, it's 2, yes. So what would be the formal charge?
-1.
-1. Anyone confused with this? Okay, so that one has -1. Repeat the same calculation, you will find that this one has a +1, and oxygen is going to be 0. Repeat it for the second low structure. It's going to be positive here, negative here, and 0 on the nitrogen. Repeat it for the last one. It's going to be positive here, and positive here, and 2 negative on that one. Which one is the least stable one?
The one on the right side.
Yes, that one, the last one, is the most further from 0, so that's the least. Negative formal charge has to be on the electronegative atom, right? So
Yes.
here, negative formal charge is on oxygen, which is the more electronegative atom. So that one here is the most stable one. That one here is the next, and that one here is the least stable one, right? So in terms of probabilities, we would say that one in the middle is like 50–60% probable. That one here is like 30%, and that one here is like 10 or 5% only. That concludes the discussion about low structures, resonance structures, and formal charge, right? Later on, we will discuss what's the problem with low structures. Low structures are very useful, as we can see, in describing the actual connectivity. For example, it told us here that nitrogen is in the middle, not oxygen, right? And if you measure the actual structure of that compound, you will indeed find that nitrogen is in the middle, right? And it tells us what type of bond links to expect, because if it said that this should be a single bond, you should expect it to be longer than if the low structure is telling you that it's a double bond or a triple bond. So it gives us really useful information, but it has problems. And the problems with low structures, which is what we will discuss in the next lectures, is actually about their shape, their prediction for the molecular shape, right? For example, water, low structure is telling us that this is the correct low structure of the compound. But if you think about it, what shape does the low structure imply? Should the water molecule be linear, or 90% angle between the two hydrogens, or what is the angle between the two hydrogens? Low structure doesn't imply anything. You might be kind of deceived to think that it's linear from the way of drawing the low structure like this, but it's actually, there is nothing in the low structure that tells you what's the shape of the molecule. The shape of the molecule is not something trivial. It's gonna determine a lot of properties later on, okay? It's really important to understand in order to understand the molecular properties later on. So water molecule, for example, is actually indeed not linear. It's a bent structure, but the angle is not 90 degrees. It's 104.5 degrees. So why does it have this angle? Why it's bent to start with? This is what we will discuss when we discuss molecular shapes later on. but it's just, it is really important to emphasize here that neither low structure description nor the orbital overlap model that we described earlier is able to explain the shape of water molecule. Low structure doesn't imply any shapes, but it could deceive you into thinking that it's a linear compound. Orbital overlap could make you think that it has to be 90 degrees angle, because if you think about it, the electrons that will be shared to form the bond are actually in two separate p orbitals. If you go back to the electronic configuration of oxygen, it's going to be 2 electrons in one p orbital, single electron in another p orbital, and a single electron in a second p orbital. So there are 2 different p orbitals used in that bond formation. Any 2 p orbitals are actually 90 degrees with respect to each other, because each one of them is running along one of the axes. One of them is going to be along the x-axis, second one is going to be along the y-axis. So it has 90 degrees. So if you think this way, the molecule should have 90 degrees between the oxygen-hydrogen bond using one p orbital and the second oxygen-hydrogen bond using the second p orbital on the oxygen atom. So it should have been 90 degrees, which is not the case, as I pointed out earlier. So none of these 2 ways of describing molecules is able to explain the shape. So we'll leave that shape discussion to the next time. One final thing that I want to emphasize, it is the polarity of the bond, or what determines the type of the bond to expect. The type of the bond to expect in any combination is going to depend on the difference in electronegativity between the 2 atoms involved in that molecule. So if you have 2 atoms that have similar or very close electronegativities with different in electronegativity that is less than 0.4, in that case, it's going to be a pure sharing of the electrons. And the result is going to be a pure covalent bond with no can shift in the electrons towards one atom or the other, because both of them have kind of similar electronegativity. So both of them equally attracts the electron to each other. So the electrons will be 50-50% shared between them. Okay? So that's the case for something with 2 atoms with the same or very close electronegativities, like a fluorine molecule. So that's the case for a pure covalent compound. Okay? But if the difference in electronegativity is kind of significant, but still not enough for a complete transfer of the electron, or in numbers, if the difference in electronegativity is between 0.4 and 1.9, the electrons will be shared, but not equally. Because in this case, one atom will have much less weaker electronegativity, much less attraction for the electrons than the other. So the more electronegative atom will be pulling the electrons towards itself a little bit stronger. So the bonding electrons will be kind of localized more on fluorine than on hydrogen. So that will make the fluorine slightly more negative and will leave hydrogen slightly more positive, as we represent here with a delta minus, a delta negative or a delta positive charge on each end. That situation here is called a polar bond, right? It's actually forming a dipole moment, an electric dipole moment, with an object with a positive end and a negative end. In physics, an object like this is called an electric dipole moment. And we usually represent the dipole or the polar molecule in this case with a dipole moment that runs from the positive end to the negative end of the molecule. Okay? If the difference in electronegativity is larger than 1.9, then this is a straightforward complete electron transfer from one atom to the other to form a completely ionic compound that is held together with the ionic bonding, electrostatic attraction between the different ions. Electronegativity is a really important factor here because it's gonna tell you what type of bonding to expect in any combination of two atoms, whether it's a pure covalent bond, polar bond, or a completely ionic bond, depending on the difference in electronegativity within these ranges that we discussed right here. And the importance of this whole discussion here is not just only to predict what type of bonding to expect, it's actually that the polar compounds are actually completely different than covalent compounds in the sense that they are actually having an electric dipole moment, as we said, which will make them susceptible to electric fields. It's gonna be, if you put a compound that is polar like this in an electric field, is gonna orient itself so that the negative end will be towards the positive electrode and the positive end will be towards the negative electrode. So it's gonna significantly affect, this is delta negative, this is delta positive, and that's how it will orient itself. And that is gonna affect a lot of other molecular properties that we will discuss later on. It's gonna affect solubility. Something polar is gonna prefer to dissolve in polar solvents. Something non-polar or covalent is gonna dissolve in a non-polar solvent, and so on. Okay, so it's gonna affect a whole set of molecular properties, even macroscopic properties like boiling, whether the compound is in liquid phase or a gaseous phase at room temperature. A lot of these properties that are actually important in daily life and in industrial processes are gonna depend on the actual nature of bonding in a given compound.